So am I audible?
Yes, ma'am.
Yes, ma'am.
Okay, fine. So in a vector space, you know that the very first thing is that additive closure and multiplicative closure. So these are the first things you are seeing in a vector space. So the operation should be closed under addition and closed under multiplication, right? Just give me a minute. The cursor is not working. Just give me a minute. The cursor in my tab, pen tab is having some issues. Just give me a minute. I'll see what's that.
Okay, ma'am.
Okay, now it's fine. Sorry for the delay. Okay. So in vector spaces, you know that the first one is additive closure. So this is additive closure. What is additive closure? If you take any two vectors from the vector space V1 and V2 and you add them, it is again in the vector space V. And what is multiplicative closure? Here it is actually scalar multiple. So multiplicative closure closed under scalar multiplication. Multiplication here, remember, it is scalar multiplication we are referring to. Multiplicative closure. It means when you do scalar multiplication to a vector, then scalar multiplied vector also belongs to the same vector space. So these are the first two properties. And once you verify scalar additive closure and multiplicative closure, then you look at all these axioms, right? So the first four axiom corresponds to addition, and the fifth and sixth corresponds to scalar multiplication, and these are associative properties, right? When these are combined, what happens? Associative property, right? Okay. So now to prove that a set is a vector space, you need to verify all the axioms starting from additive closure and multiplicative closure and all these axioms. And if you have to say that a vector space, a given set is not a vector space, it is enough to say that any one of this axiom fails. Okay. So if any one of this axiom fails, then you can say that the given set is not a vector space, right? What are some vector spaces you have seen? Can you tell me? Any examples of vector spaces which you have seen?
Matrices,
R2,
R2, R3,
R2, R3 in general,
R3,
Rn, right? Okay. So these are some familiar vector spaces you might have seen. We will see maybe one or two other vector spaces too. Okay, so what are subspaces? Subspaces are first of all subsets of non-empty subsets of a vector space, which again are closed under addition and scalar multiplication defined in V, right? So suppose you consider V is equal to R2. Can you give an example for W, a subspace?
1001.
1001. It is a set, but is it a subspace? So this, what you are saying, this is just a subset. This is a subset. But is this a subspace? See, subspace means it should be closed under addition and scalar multiplication. If you add these two vectors, what is the resulting vector? 1, 1. Is it there in this set? No. Right? So this is not a subspace.
It's a linear combination.
So all possible linear combinations should be inside that, right? So addition and scalar multiplication.
Excuse me, can you please explain why is it not a subspace?
See, a subspace means it is closed under addition and scalar multiplication. It means what? So if you take two vectors W1 and W2 from W, then the sum should be inside W. Similarly, if you take any scalar, that is any real number, then C times of any vector in W should be also in W. Now, for example, if you take this, so if so let us say this is your W1, this is your W2. Is W1 plus W2 there in W?
Yeah. Okay.
It's not there, right?
I can
One
give.
is not there.
So it can be
If
x
we,
comma
but if we,
x comma 0, where x belongs to real number.
Sorry?
Um, it can be a W can have x comma 0, where x belongs to real number.
Yes. So if you take W to be the set of all x comma 0 where x is a real number, then in this case, you know that this is a subspace. Okay? Okay, fine. So this is an example of not a subspace. This is a subspace. All right. Okay. So you know that a proper subspace means one which is, first of all, it should be a proper subset. You know what is proper, right? So it should not be equal to V itself. Okay. So what are the trivial subspaces for any vector space? The whole vector space itself and the zero vector, right? So these are the trivial subspaces for any given vector space. Okay. Apart from that, there may be some other vector subspaces as well. But always these two are the trivial subspaces for any given vector space. Okay, fine. So now for R2, what are the non-trivial, apart from these two subspaces, what are the non-trivial subspaces of R2 in general? Okay, so any line passing through origin is a subspace. Okay, whatever other subspace you think of, for example, you see here. So now this is a line passing through origin, right? So this is just simply the x-axis. So similarly, if you take any line passing through origin, that will form a subspace. And those are the only subspaces, non-trivial subspaces of R2. Okay, under usual addition and multiplication. Okay, and what about non-trivial subspaces of R3? All lines passing through origin. Similarly, all planes passing through origin. Okay. So can you give an example of a plane passing through origin? Line, you know. What about plane passing through origin?
X plus y plus z, z equals to 0.
Yeah. So if you consider x plus y plus z is equal to 0, yeah, this is, so set of all x comma y comma z. Sorry, what's happening? Okay. So if you consider set of all x comma y comma z in R3 such that x plus y plus z is equal to 0. Now this is a plane passing through origin. In general, you can think of any set
ax plus by plus cz equals to 0.
right with a, b, c in R. So this forms a subspace. So these are all planes. Okay. And what are linear combinations? Linear combination, we have seen it in a very small space, I guess in week 1 itself. So what are linear combinations of vectors? So if you have a set of n vectors, then the linear combination is the summation of alpha I vi, right? So for example, if you have these two vectors, so you can put 2 times of this plus 3 times of this. What is the resulting vector? Quickly. So minus 2 comma 2
over 2 will 6
plus
to 6 over 3.
So what is the resulting vector? What is the resulting vector?
4, 5.
4,5.
Oh,
4,5.
okay. So it is, what is happening? Something wrong with my pen. This is 6, 3. So the resulting vector is 4, 5. Right? Okay. So now you can say that 4, 5 is a linear combination of -1, 1 and 2, 1. Okay, fine. Now just a graphical geometrical view here. So here you see that you are having two vectors x1 and x2. So x1 is the vector -1, 1 and x2 is the vector 2, 1. So here this point is your -1, 1 and this one is 2, 1. Now you know that according to parallelogram law, the sum will be forming a parallelogram here. So instead of just taking the sum of these two vectors, now we are considering scalar multiples of these two vectors. So here they are considered C1 as 2 and C2 as 3. So 2 times of the first vector plus 3 times of the second vector. So the resulting vector, what is the resulting vector? So first of all, 3 times here is 6, 3. So this is 6, 3 and here you are having -2, 2 and this vector, the resulting vector is 4, 5. Right? Whatever we have done here, just we are visualizing here. Okay. So all the linear combinations, you see that they are going to lie in the same plane. Okay. Fine. Now what are independent and dependent vectors? So you can easily see that these two vectors are independent of each other, right? They are in different directions. So when you are considering two vectors and they are in different directions, what does that mean? One cannot be written as a
Linear combination of
Another one.
okay. When you are talking about only two vectors, linear independence means you are actually talking about whether they are multiple of each other or not. Because linear combination here, when you are having like the third vector, then you say that this vector is a linear combination of these two. But now totally only you have two vectors to talk about. So it means you are checking whether you are able to write V as alpha u or not. This is what you are checking for independence when you are having only two vectors. Okay. So in this case, V is not equal to alpha u for any alpha. Okay. But in this case, V is equal to alpha u for some alpha. Correct?
Yes, ma'am.
Okay. So in this case, you say that these two vectors are dependent. And in this case, we say that these two vectors are independent. This is for two vectors. Now, suppose you are having three vectors, u, v, w. So now in this case, you see that u and v lie in a plane, but the third vector lie in a different plane. It is not lying in the same plane. So u, v, w, first of all, u and v, if you take, they both are lying in different direction. Similarly, this v and w, they are in different direction. Similarly, u and w, they are also in different direction. So any two vectors here are linearly independent. Also, you see that the three vectors do not lie on the same plane, right? So the three vectors do not lie on the same plane. Hence, you can say that these three vectors are linearly independent. But here you see that all the three vectors are lying on the same plane. So what can you say about the set UVW? It is linearly
dependent.
Dependent.
okay. Now what about U and V? Or
They are
Dependent.
linearly
W?
independent.
Yeah. So if you
Dependent.
take any two vectors, this forms a linearly dependent set. Sorry, linearly independent set. But when you consider,
Ma'am,
yeah,
is it necessary that they become linearly independent? I mean, it is possible that they are linearly dependent also if they all fall on a same line, or like in a three-dimensional, we are not perfectly
Can you
visualizing
give
it.
an example, ma'am?
see, whenever you are having, for example, you take this itself. Now, suppose you are considering Let me choose another color for explaining. Okay.
So, like a professor told us in video that if we have, let's say, five vectors that, let's say three vectors which are linearly dependent, then any greater subset of it, a superset of it, will also be linearly dependent. So
Yes.
we are saying that three vectors are linearly dependent.
Hmm.
It is possible that two of them are also linearly dependent.
See, that is true, but here the picture is very clear. They are
Yeah,
not lying on the same line. Only in this scenario I am talking.
okay.
Okay. For this particular picture, I have given this. Okay. What you are saying is correct. So, for example, it can be something like, maybe if I am considering another vector, let us say z. Now, if you consider w and z, these two are linearly dependent, right?
Yes, ma'am.
Okay,
Exactly.
fine. So, geometrically, any two vectors that lie on the same line and any three vectors that lie on the same plane are linearly dependent. Okay? Yeah,
Ma'am,
yeah.
I didn't understand this. The three component wala. B, W, and U.
This
This
one.
one is. Yes.
See what happens here. You saw that now this is a third vector, right? 4 comma 5 is the third vector. So you can imagine like these are u, w, v. So these are these vectors now. For example, let us say this is your u, this is your v, and this is your w. Okay, let us think that suppose these are your u, v, and w, for example. Okay, then what happens? This u, v, and w. So W is nothing but a linear combination. Here, in fact, it is precisely C2 times of U plus C1 times of V. So this is a linear combination of these two. You see that when there are three vectors lying on a plane, the third vector, you can form a parallelogram and see that that will be a linear combination of the two other vectors. Okay.
Okay, ma'am.
So always whenever there are more than two vectors on a plane, so that will form a linearly dependent set. Not just three. If you take three or more vectors that lie on a plane, three or more. Okay, if there are more than three vectors on a plane, then that will form a linearly dependent set. Okay, fine.
Ma'am, one more question regarding that graph only. Suppose if two vectors V
Mm.
and W are overlapping with each other,
Mm.
then what scenarios can we make out of it?
See, if they lie on the same line, then those two vectors are also linearly dependent because they are scalar multiples of each other.
Okay.
Okay, fine.
Ma'am,
Yeah.
please, yeah. Ma'am, in the independent case,
Mm.
V and U are on the same plane.
Yes.
Vector V and U.
Yes.
So, vector V and U are dependent.
See, as we saw in this case, now go back to this. Whenever you are having only a plane and only two vectors, go back to this condition.
Okay.
So they are in different directions, so they are independent. If they are on the same line, then they are dependent. So now they are on the same line or are in the different direction.
They are on the different direction.
Hence, U and
So,
V are linearly independent. That's all.
okay. So, what if all the three vectors are from different planes? Suppose you are from plane 1, V is from plane 2, and W is from plane 3. And
Then
these
very
three,
good. They are linearly independent. They are
they
all
are
from different planes, so very good, linearly independent. So
okay.
first of all, they should not be in the same direction. That is the point. If they are in different plane, then
Yeah.
very good, they are in different directions. So you can say that. Okay.
Okay. So even if any two vectors
Mm.
are in different direction but on the same plane, then
Then,
also they are independent. And if all the three vectors are from three different planes, then
mm.
they are independent. Only they are dependent if, but does this isn't a little bit confusing? If in the dependent case we are
See,
considering U, V,
I
and
guess
W
I guess
are on
you
the
are
same plane.
thinking too much for now. I guess the point you should remember is that we will go step by step. Don't confuse yourself too much for now. If you are given with two vectors, you use this step. If you are given with more than two vectors, like for example, let us first talk about three vectors. then you go with this rule. Now, if there are more than 2 or 3 vectors, we will go to the next step. Hold on. Okay.
Okay.
Fine. So what is linear dependence and independence? So linear dependence means, so if you are given a set of vectors v1, v2, vn, so this set we are calling it as linearly dependent if you can find scalars not all 0 such that alpha 1 v1 plus alpha 2 v2 plus alpha n vn is equal to 0. Okay, so here not all 0 is important. It means what, at least some of these scalars should be non-zero. Okay, so for example, suppose you are considering this set. So now, is this set linearly dependent or independent? This set together.
Linear dependent.
Linearly dependent. Can you tell what are the possible coefficients you can consider?
Now we can write
So
one
that,
vector as a linear combination of other two.
okay, that is one way according to this definition. So what are the scalars you can find so that you have this kind of an expression? Let us say this is your v1, this is your v2, and this is your v3. So what are the scalars you can find which are not all 0 such that this is equal to 0? What is your alpha 1? Alpha 3. What is alpha 1?
1.
Alpha 2?
1.
Alpha 3?
0.
Okay, at least some of this coefficient should be non-zero. So now you can clearly see that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is equal to 0. Okay, but for a linearly independent set, this is never possible. So for non-zero coefficients, this expression can never be 0, right? So whenever you have such an expression, that should imply that all the coefficients are equal to 0. Okay, so that is linear independence. Okay, so if a set is linearly independent, then the only linear combination of these vectors that can yield a 0 vector is when all the coefficients are 0. Okay, fine. Now, what are the ways of checking linear independence? First, let us look at R2. So if you take any subset of R2, and if that subset is containing only the 0 vector, then S is linearly independent or dependent?
Independent.
Independent.
Independent. Okay. Now, what is 1 times of 0?
0.
So I have a non-zero coefficient and the scalar multiple of that is 0. So now according to this definition, I have a non-zero coefficient where this is 0. So is it linearly dependent or independent?
Dependent, ma'am.
Dependent, right?
Yeah.
Okay, be careful. So whenever you see a set which has the 0 vector, so that set is always linearly dependent. Okay, whenever you consider a set which has the 0 vector, even if it is only the 0 vector, the set is always linearly dependent. Okay, so if you have a vector v which is not a 0 vector, okay, now v is a non-zero vector, then what can you say about S?
Linearly independent.
Definitely linearly independent, right?
Ma'am, I just want to ask one question. Ma'am.
Yeah.
There is this one condition that we studied about this, the cardinality and the dimension. If in that case, if the cardinality is less than dimension, still it
Hold
can
on,
be-
we have not. Oh, hold on. See, you may know about dimension, but in this live sessions, we have not yet started dimension. So let us first start dimension, then you ask this doubt. Okay, please. Okay, so let us continue. Okay, if S is equal to V1, V2. Okay, now if this set is having 2 vectors from R2. Okay, what is the first method to verify linear independence? Simply check whether one is a multiple of the other. For example, you see that you have 2, 3, and then you have minus 10, minus 15. So are these 2 vectors linearly independent or dependent?
Dependent.
So these are linearly dependent. Now what about minus 1, 1, and you have 5, minus 6?
Independent.
Independent.
Linearly independent. Simply check whether one is a multiple of other or not. So you are done. Yeah. Okay. And the next method is the determinant method. Obviously for R2 you don't need this method, but anyway you should know that this method is there. So the same vectors let us consider now in the matrix form. Now what is the determinant of this matrix, can you tell?
0.
0.
Right? And what is the determinant of this matrix?
Non-zero.
One,
Right?
ma'am.
1.
So 6 minus 5
1.
is 1, so it is non-zero. So you can use determinant method also. So for R2 you can straight away tell it, but you should also know that from determinant also you can tell. Okay,
Ma'am,
fine.
for s is equals to 0,
Mm.
can't I claim 0 times 0 is also 0? And
Yes, that
hence,
is
That only
also
does.
possible.
and
Yes.
hence it's independent.
See, if
I
there
also
exists,
that.
here the condition is that there exists. If you are able to find some non-zero value, then automatically it is dependent. It does not matter. Obviously, if you put all zeros, anyway, this expression is going to be 0. That is not the priority here. The priority here is to find non-zero
Yeah,
values.
okay. If it exists, got it.
Yeah.
Ma'am, excuse me, ma'am. I
Yeah.
have some basic doubt. Please don't
Yeah.
mistake me. You said that SB a subset of R2. R2 means it is denoting that two columns it will be, right? R2
See,
means.
R2 means it is the set of all, let us say, x comma y, which has two coordinates, x comma y in R. This set. So for example, this 0 represents 0 comma 0.
0.
This v represents v1 comma v2. Right here, this v1 maybe represents x1 comma y1. This represents x2 comma y2. Okay.
Okay.
Fine. Okay. So now if S is a set with 3 or more vectors, then S is
Dependent.
yes. This set should be linearly dependent. All right. Now what about a subset of R3? If S is again 0, then S is
Linearly dependent.
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 If S is a non-zero vector,
Independent.
independent. Okay. Now what if S has only 2 vectors?
Independent.
Then we
It
have
is
to check if one is the multiple of the other.
yes. You can check whether one is the multiple of the other.
Then independent.
So
Then
here if you see that, if you have 2 vectors, now we are in R3. So for example, you see that 1, 2 and minus 3, let us say, and then you have 5, minus 6 and 7. So are they linearly independent or dependent?
Independent.
Linearly independent. What about, let us say, 5, 0, 3, and then here you have minus 1 by 5, 0, and minus here, what is the value you should have so that it becomes linearly dependent?
minus 3 by 5.
Minus 3 by 5.
Minus 3 by
Minus
3
1
by
by
25.
minus 3 by 25.
3 by 25, right? Okay.
Yes,
So
ma'am.
in this case, you see that this and this vector forms a linearly dependent set. All right. If S is v1, v2, v3, so if you have more than 2 vectors, suppose you are having 3 vectors, now we are in R3, remember that. So now what is the first method? Check if one vector is a multiple of other or a linear combination of other vectors. There can be scenarios where you can have very simple scenarios like this. Now, can you tell whether any one of the vector is a linear combination of the other vectors?
Third one.
Yes, ma'am.
Third one, V3.
So,
Third one.
suppose you call it V1, V2, V3, then you can easily see that V3 is minus 1 times of V1 plus or minus 1 times of V2, right? So, this is a linear combination of the other two. Now, I am giving something like this. Now, can you tell whether one is a linear combination of the other vectors or not?
V1 and V3. B1 and B3 are
No.
multiple of
B3.
each other.
No. B3 can be represented as linear combination of B1 and B3.
Okay, see, sometimes it is not very like immediately visible.
Correct.
In that case, prefer method 2, the determinant method. Simply find the determinant of this and you will find the answer. So if you are having vectors v1, v2, v3 from R3, okay, form a matrix A with v1, v2, v3 as the columns of the matrix. Okay, so if determinant of A is equal to 0, then you will see that this vector v1, v2, v3 is forming a linearly dependent.
Dependent.
And if it is non-zero, then you know that this set will form
They are linearly independent.
yeah. So this set is a linearly independent set. Okay. So whenever it is not very straightforward, simply go to the determinant method. All right. Okay. So if a set, so now we are in again R3, remember. So now in R3, if a set has 4 or more vectors, then S is
Dependent.
Dependent.
we are going quite slow. It's okay. As long as you all understand the concept, it's fine. Okay. More generally, if S is a subset of R, and now we are considering a subset of Rn. If S is equal to 0, then S is linearly
Dependent.
and if we are considering a single non-zero vector,
Independent.
Independent.
and if
About
we
the
are
zero
considering,
vector.
sorry,
So about the zero vector, we are saying if a zero vector exists in the set, then we are declaring it dependent. And we also know that every vector space needs to have the zero vector.
yes.
So does that mean every vector space is basically an independent set?
If you are considering the vector space, obviously it should be a dependent set, right? Because vector space is going to consider contain all the vectors.
Right.
Yeah, fine. Okay, if S is v1, v2, so check if one vector is a multiple of other. So in that case, you just have to check whether one is a multiple of other when you have two vectors. If S has exactly n vectors, then you have to use determinant method, which you already know. If S is a set with k vectors where k is any number greater than or equal to n plus 1, then S is always linearly dependent. Okay, so these are the basic things you should know about any subset of Rn. Now, if a set contains a zero vector, it is always
Linearly dependent.
linearly dependent. A superset of a linearly dependent set is
Always.
okay.
Ma'am,
Yeah.
so can we use reduced row echelon form to check the dependence or independence? If
Which method?
we have reduced row echelon form of the vectors returning exists.
Yes,
and
that also you can use for verifying linear independence. I'm going to tell it next. Okay.
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 Ma'am, regarding this one statement, ma'am, this if S is a set with k vectors, this k greater than equals to n plus. Now, if the set is having only zero vector one, ma'am, so then the k value of k will be 1, and n is greater than this. This was my doubt, ma'am.
See, k is greater equal to n plus 1 is the condition. If your set is having only one vector, so n can be, so n is usually any number, any natural number, first of all, right?
Correct.
So now if starting from 1 itself you are taking, so if you are taking one vector, it is not satisfying this condition, right?
No, that was what I was asking earlier. This cardinality and dimension thing is not satisfying this if S equals to this empty set.
Yes, you are considering an empty set.
No, ma'am, this zero vector you are taken like.
Yes. So this is considered containing only one vector. How is 1 greater than n plus 1?
So, ma'am, that one is single element. I mean that zero is not exactly zero. That contains a vector that have n values, and that is the n here written r raised to n.
See, you should not get confused. See here, this 0, for example, if I am talking about R4, if I am talking R4, this 0 vector means 0, 0, 0. But here what I mean is that, suppose you are having, for example, here itself I wrote, right? So for example, now This is one vector, this is one vector, this is one vector. Here you are having three vectors. I am not considering the components in each vector here. So suppose I am having another vector here, for example, V4. So suppose I'm having 7, 10, and 15. So this is V4. So now there are four vectors. So now your K is 4. Here you are in R3. So your N is equal to 3. So your K is greater than or in fact equal to N plus 1, right? So
Yes.
this set is linearly dependent. Do you understand?
And this is what I'm asking. When the value of k is there 1, and all the values you said is greater than, so you taken the set R2, R3, and R4, which is greater than always 1. So this condition is, this statement is not satisfying in that case. S is
I
linearly
don't
dependent.
understand your question. What it is not satisfying?
Suppose you take S equals to 0 vector set, the value of k will be 1. So the
Yes.
coordinate of, and you take it as a subset of R2, R3, or something. So it will be always
Okay.
n plus 1 will be greater than 1 only now. Then how, ma'am, this S set is
N
going to
plus
be
1,
linear?
how it is greater than 1? N is a natural number. How can this be greater than 1? So suppose N is 1 or 2 or 3. So, okay, fine, the other way around. Suppose your K should be greater than 1. So you are saying 1 is greater than N plus, greater than or equal to N plus 1. How is this possible? How 1 can be greater than N plus 1?
Ma'am, he is asking that about the zero vectors, that the zero vector is always linearly dependent, right? So if it is linearly dependent, then the case is not valid here. Like if we
See, you
take
are not
zero,
talking about like, see.
Uh,
Okay. I understand your question
so
now.
if a zero
Yes, ma'am.
vector,
Hold on.
it's a
Let me
non-zero space.
let me answer his question. See, here you are saying in this condition the set is linearly independent, but this does not say that this is the only condition under which your set S is linearly independent. Okay, so under this condition also your S can be linearly independent, linearly dependent. There are several cases where S can be linearly dependent. This is one such scenario. Okay, this is another scenario. Here, if it is a multiple of each other, then again it is a linearly dependent set. This is another scenario. Okay, these are different scenarios. This does not say that only this, under this condition the set will be linearly dependent. That is not the statement here.
yes, ma'am, that's what I was asking. Means this scenario don't have any intersection with each
Ah,
other. Means
No.
yes,
if
yes.
one follow, it's okay, and if another don't follow it, then it's okay, right?
Yeah.
Got it, ma'am.
This
And
Okay.
this,
property is also hold for a non-zero vector space. This is a zero vector. Zero is always a linearly dependent.
no, but it is
Okay.
not mentioned over there, no, like in the statement. It is,
Where it is not mentioned?
no, ma'am, this you said that this S equals to 0 vector will not satisfy this statement. So,
Yes. See, this is the condition you are talking about. If this condition is not there, then why you are going to this statement first of all?
okay, ma'am, got it.
Okay, only when you are in this condition you go to this statement. So if we are talking about, suppose let us say determinant method, in this case will it work? It will not work, right? So you have to look at the first the case. Only that case you should go to the particular method. Okay, fine.
Could you please explain what superset subset means? I can got it. What
Okay, fine.
superset means?
Where is the terminology I have used? I have used it.
It was down, ma'am.
Okay.
It was
Okay,
done.
Yeah. Okay, fine. So you see that, okay. So A subset of B. Okay. So you say that A is a subset of B and B is a superset of A. That's all.
Okay.
Fine.
Okay.
The one which contains the other is a superset.
Okay.
Okay. The subset of a linearly independent set is
Linearly independent.
linearly independent. Yes. Okay. Fine. Checking linear independence using homogeneous equations. So the other way to check linear independence is to just consider the given set of vectors, put them as columns of a matrix and call them as V. Now consider this system Vx is equal to 0. Okay. Now you use Gaussian elimination and see if you are able to solve it and see that only solution is trivial solution, then it is linearly independent. And if you get the non-zero solution, that means you are having infinitely many solutions. In that case, that set is going to form a linearly dependent set. Okay, and of course, if V is a square matrix, then you don't have to do Gaussian elimination at all. Simply use determinant method. That's all. Okay, so these are the techniques for, like I told you, the geometrical way as well as the procedure using the definition, and also here some other techniques for checking whether a given set of vector is linearly independent or not. So now you should not have any doubts regarding checking whether a given set is linearly independent or not. All right.
Just one thing. These last two statements above this thing, subset of linearly dependent. So same thing cannot be said for a subset of linearly dependent set is linearly dependent. We cannot say
Sorry.
Always.
a subset of linearly dependent set is not always linearly dependent. Am I right?
Correct. Correct.
Union
Correct.
of union of that
See,
union of that set is
for example, if you are considering, for example, if you are considering maybe this set, for example, let's say 1 0 0 1, and then what's wrong?
Your pen is not working.
Sorry, something is wrong with my pen today. I don't know. Okay, so you are having 1 0 0 1, and then let us say you are having maybe 1 1. Now in this set, so this set is linearly dependent or not?
Yes.
Yes. Yes. It is.
Now if you take any subset of this, so is it linearly dependent or independent?
Independent.
So if you take any
Dependent.
proper set, if you take any proper set, it is linearly independent always, right? So any proper subset of this is linearly independent. So proper subset is linearly independent. But suppose if you are considering, for example, 1 0 minus 1 0 and 1 0 1. Now if you are considering, let us say this is V1, this is V2, and this is V3. Now suppose you are considering V1 and V2. So if you are considering this subset, now this subset is linearly dependent or independent?
Dependent, ma'am.
Dependent.
Dependent. Now what about V2 and V3,
Independent.
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 right? So a subset of a linearly dependent set may be linearly dependent or may be linearly independent. We cannot guarantee anything. Okay, fine. You have to just look at the set and decide. All right. Okay, so finally week 4 after almost an hour now. Okay, span of a set. The span of a set denoted by,
Ma'am,
yeah,
just a question, please.
yeah.
In you have to talk about the linear homogeneous equations.
Mm,
If the homogeneous equations are not a square form a square matrix, it may
mm.
be variable are more than equations or
Yes.
variable are less than equations. Then they we have always checked by the echelon form, or there is some another conditions also.
Echelon form is the best method because that is what is the only method we have seen for non-square matrix.
Non-square matrix, either variable are less or either variable are more.
Yeah, yeah, yeah,
Okay, thank you.
yeah. Okay.
One more doubt.
Yeah.
We have to represent the set of those vectors at the column of the matrix.
Yes, yes. Okay, you have to write them as columns of the matrix. Okay. Uh, can you just give me one moment? I'll be back. One moment. All right. So here the span of a set denoted by, what is span of a set we are going to see. See, what is that we are doing here? First of all, overall idea, I'll just tell you. Okay, so we first saw few matrix techniques in the first 2 weeks. Okay, then in week 3 we have seen like vector spaces and what is linearly dependent and independent. So whatever matrix techniques we have seen in the first few weeks, we are going to use in week 3, week 4. You see, for understanding linear independence and dependence, we have used this concepts from week 1 and week 2. Okay, so week 1 and week 2 are kind of preparing to understand the upcoming concepts. Okay, the matrix concept. So now week 3 we have introduced what is a vector space, and then we are now trying to understand the elements of the vector space, which are vectors. So what happens when vectors are lying in different directions or in the same direction? So that is what we have understood so far. So understanding the arrangement and what is the effect of the uh, arrangement of the vectors. Now in this week, what we are going to see is that we are going to see now what suppose you are having some specific vectors. So how can this specific vectors help us to understand the whole vector space? Because the vector space has how many vectors? Can you tell? Any vector space, forget about the zero vector space. Apart from the zero vector space, how many vectors are there in a given vector space in most of the cases? Let us say in Rn. Any Rn you take, how many vectors are there?
Infinite, ma'am.
Yes, there are infinitely many vectors, but is it possible to study each of these infinitely many vectors? It's not that easy, right? So to understand or to talk about the whole vector space, it is easier if that whole vector space is represented by a small set of vectors, right? So that is what we are trying to do in this week. So instead of studying the entire vector space, now we are going to consider a smaller set, very smaller set comparing to the entire vector space, which can actually represent the entire vector space. This is what we are going to do in week 4. This is a very rough idea of what we are going to do. Okay, fine. With this, let us start. What is span of a set? Okay, the span of a set denoted by span of S is the set of all finite linear combination of the elements of the set S. So that is span of S is here. So suppose S is having the set of vectors V1, V2, Vn. Okay. So now span of S is the set of all possible linear combination. I is equal to 1 to n, alpha I, Vi. So these alpha I can vary over R. Okay. So for example, if my set S is singleton set, for example, maybe I'm talking about 1 comma minus 1. Now can you tell what is span of S?
A into 1 comma minus 1.
2.
Yes. So A into 1 comma minus 1, where A is a real number. So it means here you are talking about all A comma minus A, where A is in R. So what does it represent in R2? Can you tell? What does it represent in R2?
A line.
This set.
Line in the third coordinate.
Yeah. So this you see that if your set S is 1 comma minus 1, the span of S is this set. So the span of the set 1 comma minus 1, can you tell what is exactly the equation of the line? Y is equal to?
Minus x.
X is equal to minus y.
Yeah, or y is equal to minus x, anything. So this is the line represented by the span of this set. Okay. Also, there is one thing you should remember that by definition, what is the span of an empty set? You know that this notation is representing empty set, right?
Yes, ma'am.
Okay. What is the span of an empty set by definition? It is the zero vector.
Zero.
This is the definition. So don't think about this much. So by definition, we are defining span of an empty set as a zero vector. Okay. Fine. What is this given in bold? Span of S is a vector subspace. How can we prove that span of S is a vector subspace? For proving subspace, what are the things we need to prove?
Zero vector lies under this and
That is
close
hold on, whatever you said, that is an important point, whether zero vector is there in the set or not. But that is when you are like trying to disprove that it is not a subspace. But when you are trying to prove that it is a subspace, straight away you see closure under addition and scalar multiplication. Okay, so now it is given as a subspace. So the first thing is that you have to prove that it is closed under addition. How do you prove that it is closed under addition? So how can a typical element from span of S look like? Summation I is equal to, let us say, alpha I vi, and here let us say summation I is equal to 1 to n beta I vi. All right, these are typical
Yes.
elements of span of S. Now what happens to x plus y?
Summation of I to n alpha I plus beta I vi.
Alpha
Alpha
into
So
plus beta
obviously you see that
into V.
this is also in span of S, correct? So it is
Correct.
closed under addition. What happens to scalar multiplication? So it is again summation I is equal to 1 to n c times of alpha I vi.
It is
So again it is in span
span.
of S. Okay, again it is in span of S. So it is closed under addition and scalar multiplication. So this is the
And can you
vector.
please explain the last point again?
So the last point, you mean scalar
C
multiplication?
into X. Yeah, the scalar multiplication. Yes, ma'am.
Okay. So the scalar multiplication, c times of x means you are multiplying c to each of this term. So you have c times of alpha I vi. That's all. The c comes in every term. So suppose you are having alpha 1 v1 plus alpha 2 v2, and then you are multiplying c with this whole term. Suppose you are multiplying now c with this entire term. So what happens? You get c multiplied with each of this term, right? C alpha 1 v1 plus c alpha 2 v2.
Then, ma'am, will it still belong to span?
Yes, because now c alpha I is again another real number. The coefficient should be a real number. That is all you need.
Okay, ma'am. I understood it. Thank you.
Okay. All right. So you see that now this is a line. Okay. And it passes through origin, of course. So span of any set S always contains the zero vector, true or not? Span of any set will always contain the zero vector, true or not?
True, I think.
Right? Because if you consider all the coefficients to be zero, then what happens? Then obviously zero vector is there in the set, right?
Yeah.
So
Yes, sir.
also it is a subspace, so zero vector of course should be there in the set. So span of S always contains the zero vector. Okay, fine. Now can you tell what is the span of any non-zero vector here? So we are considering a vector from R2. What is the span of any non-zero vector in R2?
Straight line.
The entire
1 comma
Okay.
It's
Enter R2.
yes,
1 comma 0,
except
0.
0.
Here you are considering only one point. For example, that point can be 1 comma minus 1. And we saw that the span of that point was this line. Now I'm talking about any point from R2. What is the span of that particular point I'm asking? You are saying entire R2. Is that possible?
1 comma 0, 0 comma 1.
See, first understand the question. What is the span of this set?
Span of the set is line.
Yes.
straight line. It's a straight line.
Yeah, it is a line passing through origin, right? It is a straight line passing through origin. This is very annoying.
Okay, straight line passing through origin. Okay.
Y equals to x.
It always passes. Yeah, it's always passes through origin.
So it is a line passing through origin. All right. So now you see that it is in fact a line, you can say that, which passes through 0 comma 0 and x comma y. So it is kind of the line connecting these two, right? What about the same when you are talking in R3 again?
It's the plane.
See now,
Yes,
imagine,
ma'am.
okay, let us say you are in a plane. Okay, let us say, sorry, you are in R3 itself. Okay, you are in R3. I am considering the vector 1, 0, 0. Now, what is the span of 1, 0, 0? What is the
It's
span of?
x-axis. It's x-axis.
Then how can you say it is a plane? See, span of a vector from R3, only a single non-zero vector again leads to a line passing through origin only. Okay, because you are having only one vector and you are spanning it. Spanning means you can kind of imagine like stretching or shrinking the entire vector in all possible ways, right? But only like along the line. Okay, so that will form a line only, right? It cannot form, you are not rotating here. Only you are
Can you
stretching
please?
the line. So it means you are forming a line passing through origin again. Okay, so this is a line passing through
But
origin.
I understand, but here it is stating that ABC is not equal to the origin.
Yes, it is not the origin, but it is a line passing through origin.
But ma'am, ABC can be any real number, no?
Yes, it can be any real number, but
Except
not
0, 0, 0.
yes, except this origin.
What
Then
will happen if it is origin?
how are we so sure that it is passing to the origin?
Because we are talking about the span, and just now I told you span of any set will contain the zero vector.
Okay.
Hey.
Okay, you understand?
Yeah.
Ma'am, what will
Excuse
happen?
me, ma'am.
Yeah. Yeah.
Then why this is condition is given x y not equal to 0, 0?
See, I am talking about span of a non-zero vector. If I am talking about span of a zero vector, okay, you can talk about span of one single zero vector. It is going to be zero vector. My question is just what is the span of non-zero vector? That's all. Okay.
Ma'am,
Yeah.
if we talk about the span of this zero vector, it will be R entire R3, right?
How can
Because
zero vector will span entire R3?
it can stretch in any direction.
Zero. See, it is just a point. You are doing scalar multiplication. Whatever scalar
It will
just
still
will
stay
end up with
zero.
just zero only, right? So span of the zero vector is going to give you only the zero vector. All right.
Then in term, okay, and then in the way you define for this stretching part, in that case, this zero vector will not get stretched any direction, right?
See, zero, it is just a point. It is not like
Ah,
any vector, like a line. It's not like that. It's just a point.
that
Okay.
Ma'am, span of the point is not containing origin. How it will passing through origin?
See, that is what I'm telling. Span of, that is what I told you here. Span, first of all, the subspace, it should contain zero vector. But how? Because we are considering span means, according to definition, it contains all possible linear combinations. So linear combination with zero coefficient is also considered. So it means 0v1, 0v2, 0v3 you are taking and then adding up. So you end up with zero vector. So the same here. So now you are talking about span of x comma y. First of all, what is this set exactly? It is the set of all
Non-zero.
sorry. So
Non-zero.
it is the set of all alpha times of x comma y, right? So it is the set of all alpha x comma alpha y, where your alpha is a real number. Now, if your alpha is a real number, means alpha can be zero also. So your 0 comma 0 is also here. So this line is passing through origin. Do you understand?
Yes, ma'am.
The same
Yes.
happens here as well. The span of a comma b comma c is alpha times of a, alpha times of b, alpha times of c, where alpha is a real number. That's all.
Oh, so actually the alpha remains the same. It's not that it's alpha x comma beta y.
No, 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 no. Alpha, you are multiplying for this vector entirely. This is one
But
vector.
I thought since x and y were not similar, that's why I thought it might be
See, this
like.
is one vector from R2. You cannot split it. Okay, this is one vector from R2. Okay, this is just one vector from R2 and you cannot split it. So
Ma'am,
don't, yeah.
is it spanning all the entire R2?
That is
No,
what
it's
it
just
is,
a
it is not
line.
span. It is just a line. How can it contain the other points? This point, this point. These are not there in the line, right? There are infinitely many points which are not there in the line. How can it span entire R2? Okay, fine. Okay, so now consider this set. S is 1, 1, 0, 1, 0, 0. What is the span of S? So let us write the span of S according to the definition. So span of S, so let us call this V1 and this is V2. So according to the definition, can you tell me what is span of S?
X comma Y.
Maybe first let us
Alpha
do step by step. Alpha 1 V1 plus
alpha 2
alpha 2 V2. Okay. So alpha 1 V1, alpha 2 V2, where alpha 1 and alpha 2 are
Belongs to R.
Numbers.
vectors from R.
Scalar or vector?
Scalars.
Yeah, vectors. Alpha 1 and alpha 2 are vectors. Sorry, scalars, right?
Yeah.
Oh, this pen is very annoying. I'm really sorry why this is happening.
What you are using?
Usual Wacom board which I use for any class.
Ma'am, you might have touched some buttons, ma'am. That's a problem. In the pen, some buttons are there.
I checked that.
You should not touch that.
I checked that that's not the case. I'm not touching any button, but still it's happening. I don't know.
Because I'm also having the same. That's why.
Okay, fine. Okay, so now let us write the set exactly. So alpha 1, 0 plus alpha 2,
Alpha 2, 0, 0.
alpha 1 and alpha 2 in R. Right? Okay. So now this set is nothing but alpha 1 plus alpha 2, comma alpha 1, comma 0, where your alpha 1 and alpha 2 are in R. Is this the problem with the edge I'm using? It cannot be, right?
Try it on Notepad. You will.
Okay, let me check with a different application. Maybe just maybe I'll write this problem
Sorry,
over here.
not Notepad.
I also don't think it's because of that.
Ma'am, are you having the buttons in the pen or not?
Yes, it is there, but I'm not pressing it. I made sure I'm not pressing it.
Oh, okay.
Maybe battery is low, ma'am.
Okay, fine. Let's get out of this. Okay, so alpha 1 and alpha 2, alpha 1, 0. So this is a set now. Can I replace this alpha 1, alpha 2 with some x and alpha 1 with y? So I'll simply write this set as x comma y comma 0 and x comma y in R. Alright? Okay? Is that fine? So now these two sets are representing the same thing because your alpha 1 and alpha 2 are varying over the entire R. I can simply rewrite this set in this way. Okay. So now this set is, can you tell what is this set representing?
The XY plane.
The XY plane, ma'am.
So this set is representing the XY plane. Right? It is representing.
Yes, ma'am.
The XY plane. Okay, fine. Okay, so now let V be a vector space. Okay, so what is the span of a set we understood? Now instead of starting from a set, now we are moving in the other direction. So what we did, we just took few vectors and we saw what is the span of the set. So now what we are going to do is that we are going to either consider a subspace or a vector space, and we are going to see whether we are able to find some vectors such that span of that set of vectors is this vector space. So that is the concept of spanning set. Okay, let me tell again. So suppose you are having a vector space and you are able to find a set subset of V such that span of S is V, then S is called as spanning set of V. Okay. So now the span of S is V and S is the spanning set of V. Okay. You understand? For example, here you see that for XY plane, these two vectors. So this set S is a spanning set for XY plane.
So this spanning set is not unique, because
Yes,
we can
yes, yes.
write
Yes, that is true. For example, for R2, can you tell any example, any spanning set?
1001.
Yes. 101.
Then Raj Nakhate, please mute your mic.
Can you say any other set?
1 1 and 1 1 again. Possible.
No, no, no.
1 1, and can you repeat your answer?
1 1 and again 1 1. No,
1
no, no.
1
Sorry,
and
1 1
again 1.
and 1 1 and
Yes.
maybe
-1 0. Any
yeah,
other?
minus
0 0B.
A 0 B. What are A and B? What are A and B?
The integers.
Integers. Any specific integers, or are you considering varying over a set?
Just specific A.
Specific values, then let's put specific values. In fact, you can put like this, but let's not confuse others. So maybe I can take 5 0 and 0 6. Yes, this is a spanning set. And any other apart from these zeros, maybe 1 1 1 minus 1, can you tell?
we can also take three vectors, and the third vector can be zero vector.
Of course, you can do that. So let us take S4. So S4, I am going to take the same S1, 1 0 0 1, and the 0 vector. This is also possible. Or in fact, you can take 1 0 0 1 1 minus 1. This is also a spanning set. Okay. So all these are spanning sets of R2. Okay. Now can you tell spanning sets for R3?
1 0 0 0 1 0 and 0 0 1.
Yes. Okay. What about any other set?
1 1 1 0 2 0
Okay.
and 0 0 4.
Okay. Fine. Okay. So in fact, what you can do is that for Rn, in fact, for Rn, so any set S which contains n linearly independent vectors spans Rn. Okay, it means this S is a spanning set for Rn. So here, for example, you see there are two linearly independent vectors. Here there are two linearly independent. Here, here, here. So whatever set you consider which has two linearly independent vector, it will span R2. Similarly, whatever set in R3 you consider which has three linearly independent vectors, it will span R3. It is not necessary that it should contain exactly n linearly independent vectors. It can have more than n linearly independent vectors, but n linearly independent vectors is the minimum, is the basic requirement. Okay, more than that is something extra. Okay, so here are some questions. Is the spanning set of a space unique? What's the answer?
No.
Yes.
No, no,
No,
no.
ma'am.
No, right? So the
But
spanning,
why is it no, not unique? Not unique, why?
you tell me why it's not unique. What did we just saw? We
Okay.
saw
So
some
if
examples. So we saw some
okay,
examples. S1, S2. There are we now itself we form like 5. There are actually infinitely many. So you see that there are many spanning sets. There is not like only one single spanning set for R2. There are infinitely many you can see. So that is why it is not unique. Okay.
Ma'am, I
Yeah.
have a doubt in the last statement. This for R n any set.
Mm.
So if suppose there are n plus one linear independent vectors, then it will span for R n plus one, not R n.
But in Rn, can there be n plus 1 linearly independent vectors?
Yes, it can.
Yes, it can. Are you sure?
Then that will become linearly dependent, no?
See, this is
Oh
the
yes, yes, yes.
statement I
Sorry,
told you
sorry.
here.
Yeah.
Please
Yes, yes.
recall that any set in Rn which has more than n plus 1,
Yeah.
n plus 1 or
I know that.
vectors, so that is linearly dependent. Okay.
Okay. Thank you.
All right. Okay. So here this answer is no. Okay. Let S is equal to 1, 0, 0, 1, 1, 1. Then S spans
R2.
R2. If S is equal to 1, 1, 1, 0, then S spans
R2.
then R2. Right? All right. Okay. If S1 and S2 are two spanning set of a vector space V, does S1 and S2 contain the same number of vectors?
Not always.
Not always.
So here itself we saw an example, right? So these two are spanning sets for R2, but they are not containing the same number of vectors. So the answer is no. Need not be. Need not be same. Okay. Okay, here is a question. Choose the set of correct options. If S is a spanning set of the vector space V, then S union V must be a spanning set of V for all V in V. True or false?
True, ma'am.
Yes. So if you have any superset of S which is already a spanning set, then that is also a spanning set, right? True. What is the span of an empty set? I have given the definition.
Say zero.
True.
Okay.
True.
If S is a spanning set of the vector space V, then S minus V must be a spanning set of V. Is that true?
No, ma'am.
True.
False.
No,
True.
right?
Not always.
False.
Yes.
What does this statement mean, the option 3?
Option 3, for example, suppose you are considering this set and you are leaving out one vector here, can it still span R2?
No, ma'am.
No, right? So for example, here V1, V2, V3. So S minus V3, it can still span R2,
Yes.
right? But
Yes.
here, if you span, let's say V1, V2, if you take out any one vector, then it cannot span R2, right?
Yes, ma'am.
That depends
It
on the
cannot.
scenario.
Okay, ma'am. Thank you. Got it.
Okay, if S is a spanning set of the vector space V, then S union V may not be a spanning set of V for all V in V. True or false?
False.
False, of course. Because it's contradicting the first statement, right? Okay. Let V be the subspace of R3 defined in this way. Okay. Choose the set of correct options from the following. So, first of all, let us just have a quick glance. Okay, so these are the options given to you. Okay, fine. Now here, first let us rewrite this statement here. So x is given as y minus z, y minus z, y and z, where your y and z are in R. Okay, so now first of all, are these two elements there in V? 1, 1, 0. Is it satisfying this condition?
Yes, ma'am.
So your y minus z is the first entry, second is y, and third is this. So this is your y, z, this is y minus z. Okay. So this is your y, z, this is your y minus z. Correct? Okay, so these two are entries from this set. Okay, are they multiple of each other?
No.
So are they
No, ma'am.
independent?
Yes.
Yes,
Really
ma'am.
independent.
Yes,
Independent.
they are linearly independent. Yeah. Okay, now you are having three vectors 1, 1, 0, 1, 0 minus 1, and also you have another vector 0, 1, 1. Now this is your y and this is your z, this is your y minus z. Okay, this vector is still there in this set. Now is this a linearly independent set? How can you tell whether it is linearly independent or not? Okay, let us call
By
this
seeing
V1,
the determinant.
V2. Okay, what is V1 minus V2 first of all?
It's V3.
0 minus 1, 1.
V3.
It is V3, right? 0, 1, 1.
Yeah, it's a linear combination of
So
can
this
be
is
Yes.
the
determined.
linear combination of V1 and
So it
V2.
is not independent, it's
Yeah,
It's
dependent.
not independent.
yeah. Okay, fine. Okay, now here, is this a spanning set? 0, first of all, we saw that this is already there in V. 1, 0 minus 1 is also there in V. Now, is this a spanning set? Are they linearly independent? Are they multiples of each other or not?
No,
They are not multiples of
these
each
are
other.
No.
linearly
Not in the
So
independent.
it
form.
means they are linearly independent. I have told you that.
Linearly independent.
So, okay. So, if they are linearly independent, I have not yet started the concept of dimension, but once you know dimension, answering this is much easier. So, this is a this is first of all a plane, right? This is a
Yes,
this is representing a plane.
plane.
So, remember
Yes, ma'am.
that. Maybe I will tell it to you here and we'll look at the details later. So, if you are having a line, one, okay, let us call S represents a line passing through origin, let us say. Okay, definitely it is passing through origin. That is what I'm considering. Maybe I will mention to avoid confusion. Passing through origin. Okay, so S is a line passing through origin. Now, yes, I am saying only one point, one vector, one non-zero vector. One non-zero vector from, instead of S, maybe I will put to B. Okay, one non-zero vector from V is enough to span V. Okay, now if your V is a plane and that is also passing through origin. Okay, oh my god. Okay, your V is also a plane and this is also passing through origin. Now for this you need only two linearly independent vectors from V to span R2 or to span V. Okay, so now with this, can you tell that now you are having two linearly independent vectors from V, okay, where V is a plane. So will they span V?
Yes, ma'am.
Yes.
Yes.
Ma'am, wait, is V a plane or R3? Can you scroll up?
This is a plane in R3,
Okay.
right? Because here you have an equation of a plane, right? X plus Y plus A. So here X minus Y plus Z is equal to 0 is your plane.
Okay, yeah.
Ma'am, could you show that previous statement you wrote in red? Yeah. Okay.
Okay, fine. Okay, option 4, 1 comma 1 comma 0 is a plane, is a spanning set of V. For a plane, you need two linearly independent vectors. So you need at least two linearly independent vectors. At
Yes.
least. Okay, so it cannot be less than 2. So here you are having only one vector. So is that
So this
sufficient?
is false.
Yes. Okay, fine. Now, okay. So we have seen that if you are given a set, you can check whether it is spanning the set V or not. Now suppose you are generally given a V and you are asked to find a spanning set for V. Now for example, R2 and R3, you have given some examples for spanning set. But I am giving you some other vector space which are not familiar, maybe kind of a subspace you have seen here. So where is the subspace? So this is a subspace. So like this, suppose you are having some subspaces or some other vector spaces you are having. How will you build spanning sets? Okay. So that is the next topic we are going to see. So before this, maybe I'll have a 5 minutes break and we'll continue again. Okay. We'll have a 5 minutes break and continue. So meanwhile, if I can give you some work, should be better. Okay. Okay, you try to figure out a vector spanning set for, I'm just trying to give you some subspace randomly, maybe x is equal to y plus z, something very similar to the previous one. Okay, try to construct a spanning set for this. Okay, think of what are the possible ways you are using. Maybe you can use this concept I have given you and try to consider a spanning set. We'll have a short break, 5 minutes break, where you can work on this also if you want. Okay, so let us resume. So were you able to find spanning set for this space V?
Yeah, yes. So I think we need two independent vectors.
Mm-hmm.
We need two independent vectors uh, for this.
Yeah.
This represent a plane, right? This
Yeah.
set. So we need two independent vectors to represent the plane.
Yeah. So the easiest way is that this is a shortcut. So the easiest way whenever you have such an equation is that take y to understand what is this plane. So take y commonly, you will have y times of 1 1 0 plus z times of 1 0 1. Correct.
Yes.
So now you see that these two vectors span V. So this is your V1, this is your V2. So if your S is V1, V2, this will span V. Okay, so this is spanning set for V. So there are several other spanning sets. This is one of the very straightforward spanning set we can see from the given set. All right. Okay, so formally let us look at how do you build spanning sets. Okay, fine. So for building spanning sets, we have to let us start from one vector from the set, and then we have to keep on adding vectors to that set till we get a spanning set. So let us start with R3. So for R3, let us start with the empty set. And then what is the span of the empty set? You know it is the zero vector. Okay. So now let us since span of S0 is not R3, let us add a vector. Now we are considering any random vector, random non-zero vector we have considered in the first step. So in the step 1, we consider just the empty set. Step 2, we are considering any random non-zero vector. Okay. So now what is span of S1? So span of one non-zero vector, we have seen that it is a line in R3 and it is still not covering the entire space. Okay. Now we have to choose another vector outside the span of S1. So it means it should not be a multiple of this vector 110. So you take any vector which is not a multiple of 110 and add it to this. Add in the set, you include that vector to this set S2. So now this vector 111 is any random non-zero vector outside span of S1. Okay. So now your S2 is 110 and 111 and span of S2 is now a plane. Okay. Span of S2 is a plane. So which still does not cover R3. It still does not cover R3. Okay. And we need one more vector. So for that, you are now going to consider another vector which is not there in the span of S2. So it means you should find a vector which cannot be written as a linear combination of these two. Okay. So if you now include this in this set S2, then you will get a spanning set. So you are keep on adding vectors one by one by just considering vectors outside the already existing spanning set. Okay. So this is a way to build spanning set. Okay. So how can you construct a spanning set for R3 starting with the set 1, 2, 3? This is a homework for you. So I am telling you should start with the vector 1, 2, 3 and use the above technique to build a spanning set for R3.
Could you
Yes.
Could you please explain step 3?
step 3, ma'am?
Step 3. Okay. So step 3, what happens? See, just like what we have written here. So if V is a line passing through origin, then one non-zero vector is enough to span V. Similarly, if V is a plane, then at least two linearly independent from vectors from V, you need to span V. Okay. So now here, the same thing, you can see that. So if S is one non-zero vector from R3, then span of S is a line passing through origin. Okay. So if it is only one non-zero vector from R2, then can you tell what is the span of S? Again, it is still it is a line passing through origin, right? Okay. So now this is scenario 1, and here the next case, if S has two linearly independent vectors from R3, then span of S, it will form a plane passing through origin. Right? It will form a plane passing through origin. Now, what about two linearly independent vectors from R2? Then span of S is? Can you tell? What is the span of any two linearly independent vectors from R2?
Line.
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 Already I told
Plane.
you
The
Plane
one
plane.
of the vectors
Line
Line passing through origin.
Line.
here your space itself is just one single plane. So what is the answer?
Any one line.
That one plane is R2, right? You don't have any other plane.
Line will pass, no ma'am.
The plane perpendicular to it.
I want at least one correct answer, please.
XY.
One correct. Yeah?
XY plane.
You are in R2. What is XY plane in R2?
Ma'am, the entire R2.
Yes, thank you. Okay. So here R2 is the entire space and it is the entire XY plane. Right? You don't have any Z or any other plane here. Only XY plane is what you have here. Okay. So here, if you have two linearly independent vectors from R2, span of S is going to be R2 itself. Okay. So now you see that here S2 has two linearly independent vectors from R3. So span of S2 is a plane. Okay, span of S2 is a plane, and in particular it is x is equal to y. This is not required particularly here, but you can see that that plane is nothing but x is equal to y plane. Okay, so you see that if it is just a plane, it still does not cover R3, right? Because I have already told you for R3 how many vectors you need to span the entire space. Three
Minimum
linearly.
two vectors.
Three.
At least three.
Three
At
linearly
least
independent vectors. So for R3, we need three linearly independent exactly.
Yeah.
Yeah, exactly we can say. So three linearly independent vectors to span R3.
Ma'am, but you said any two linear independent vectors can span R3, right?
Span R2. Any two linearly independent vectors will span R2, and for R3 we need three linearly independent vectors.
In that
So,
option, you have said that one come on the two before just up.
This one?
That option 3. Option
Yes.
3 is two linear independent vectors forming an spanning of set of V, right?
It is not
option 3. Option 3.
Yeah, option 3 says it is a spanning set of V, but it is not spanning R3. It is spanning this set V, which is a plane. This is not your entire R3. Okay.
It's XY, that means it's not B, not like this.
We are in R3, but it is not entire R3. It is just a plane in R3. It is a subset of R3.
That plane only alone it is spanning.
Yes,
right.
only it spans this plane, not entire R3.
Okay.
Okay. But for spanning entire R3, you need three linearly independent vectors. So far, we have only two linearly independent vectors, and we need another linearly independent vector. So to find the third linearly independent vectors, you have to find a vector which is outside the span of S2.
Okay. I thought that considering plane, and I was just confused.
Okay, fine. Okay, so using these steps, it is a homework for you to build a spanning set starting with this vector.
Like for this question, ma'am, we have to find the we have to find only two independent linearly independent.
Yes, two more linearly independent vectors.
Yeah.
It cannot be unique.
Okay, so fine. Okay, so we have not seen matrix spaces so far. So have you seen matrix spaces in week 3?
Uh, Sir told us in the live session, they gave one example of it.
Okay, so usually that one example, maybe Mn of R you have considered. Maybe I can recall it and start this exercise. Okay, fine. So Mn of R, what is Mn of R? Mn of R is the set of all n by n matrices with entries from R. Okay, all n by n matrices with entries from R. Okay, fine. So now Mn of R will form a vector space with usual matrix addition and scalar multiplication of matrices. You know what is scalar multiplication of matrices, right? So you have two matrices, you know how to add them. And what is scalar multiplication with a matrix? Suppose you are having a matrix n by n matrix here. Suppose you have A in Mn of R. Okay, and okay, A comma B, let us say. So you know what is A plus B. So A plus Bij is nothing but Aij plus Bij. This you know, usual addition. And scalar multiplication, this also you know, alpha times of Aij.
Yes, ma'am.
Right? So under this usual addition and scalar multiplication, this forms a vector space. Okay, there are several subspaces for this vector space, which we will consider throughout this course. So here is one such example given to you. So let S be the set of vectors. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So the set of matrices where, so this is the set of matrices. Choose the correct statement. Span of S is the vector space consisting of only lower triangular matrices. First of all, here, this is, let us call this as A1. This is A2. This is A3. Let us write what is span of S. What is span of S? By definition, what is span of S? Can you tell?
Upper triangular matrix.
No. Tell me step by step definition.
Summation alpha ABI.
Alpha A1, alpha, yeah.
Plus alpha A2 plus
A2
plus alpha 3 A3.
Where alpha 1 and alpha 2, alpha 3 belongs to R.
Belong to R, right? So now this is representing alpha 1, alpha 2, alpha 3, 0. Right? Such that alpha 1, alpha 2, alpha 3 is in R. Okay. So now this is a subset of M2 of R. Just to note. Okay. So now what is this set exactly? Can you tell?
Upper triangular matrix.
So this is the set of all upper triangular matrix in M2 of R.
Yeah.
Okay. Okay. So now span of S is a vector space consisting of only lower triangular square matrices of order 2. Is it true or false?
No, it's upper triangular.
Right? So option 2 is correct.
Yes.
What about option 3?
Yes, it's true. It is square matrix.
Does the span contain all the square matrices of order 2?
Oh, no, sorry.
No.
I just.
For example, this
False.
0, 1, 0, 0. Is this matrix there in Span of
No,
S?
no,
No,
no.
no, no.
No, ma'am. It is not there in span of S. So this option is incorrect. Span of S is the vector space consisting of only scalar matrices of order 2.
No,
Not
no,
true.
no,
False.
not.
Okay,
Not
No, ma'am.
suppose this word is not there. Will the statement be correct? Contains. So let us say contains. Is this true?
Yes, no, it will, yeah, it
No,
can be.
no, it is
Oh,
not.
no, no.
no, ma'am. It's not true.
But if alpha 2 is 0 and alpha 1 and alpha 3 are non-zero, then
Then it can be.
yeah.
See, let us call, I have already given names for the vectors. So A1, A2, A3 are the matrices. Now, suppose I am considering span of S is actually all possible linear combinations. Now, I am considering this specific type of linear combination. So, alpha times of A1 plus 0 times of A2 plus alpha times of A3. This where alpha belongs to R.
Yes,
This is a subset of span of S, yes or no?
yes, ma'am.
So can you say that the set of all scalar matrices of order 2 is contained in span of S? Okay. So this is nothing but the set of all 2 by 2 scalar matrices, right?
Yes, ma'am.
But it is a vector space consisting of only scalar matrices.
Yes. So the option is correct. By my question was that if the question is changed to contains scalar matrices, will it be correct? That was my question. So if it is as
Yeah,
it
yeah,
is,
yeah.
then option is incorrect. Okay. Fine. Okay. So the next topic here is basis of a vector space. Yes. So we have seen that.
Ma'am,
Yeah.
sorry for the interruption. I actually did not understood how you made that matrix upper triangular.
This
Yeah,
one.
this one.
The alpha 1 times of A1. So this first entry is alpha 1
Yeah.
plus alpha 2 times of A2. So this entry becomes alpha 2. And
Okay.
alpha 3 times of A3, this is now alpha 3. Add this everything together, alpha 1, alpha 2, alpha 3, this is 0. That's all.
Yeah, yeah, yeah. Got it, got it. Thank you, ma'am.
Okay. Okay. So far we have seen that span of a set means, so you are having a set of vectors and then you are doing all the linear combination and then you are ending up with a subspace. And then you saw spanning set means we are having a subspace or a vector space and then you are finding a set for which the span is the entire space you are considering. But that spanning set is kind of like having like various number of entries. So some spanning set are having 2, some are having 3. So like this, the number size of the spanning set is varying. Also, the spanning set is sometimes linearly independent, sometimes it is linearly dependent. So some like there are no similarities you can see, except that it contains the minimum number of linearly independent set for the given vector space. Okay, so now we are like improving the spanning set. Okay, so a basis B of a vector space V is a linearly independent set that also spans V. So basis means it should have two properties. First, the set should be linearly independent. Second, so suppose your basis is B,
It should
so
span.
span of B should be V. If both these properties are there, then that set is called a basis. Okay. So now just quickly look back. So for example, where did we? Yeah. So you see that maybe this itself we can consider. So now this is a vector space and this is a linearly independent set. Okay. And this, what is the span of this set? We have seen this also. This is a spanning set of V. Can you tell this as a basis?
Yes.
Yes.
Because it is linearly independent, it is also spans V. So you can say that this is a basis.
So all the vectors in this set should be linearly independent.
See, when you are talking about linear independence, you are talking about the entire set, not individual vectors.
Okay.
Okay, fine. Okay. What about this set? Is it a basis? Is this linearly independent?
Yes.
This is linearly independent.
Yes.
And it is also spanning.
Hmm.
So it is a basis, right? So this is a basis. What about this set? Is this linearly independent?
No, ma'am.
So this is spanning, but not
linearly independent.
linearly independent.
Totally
So
independent.
Not a basis.
okay, so you understand, right? What is a basis and what is not a basis. Okay. Okay, so now can you give some examples for basis for R2?
1,0, 1.
1001.
1, 0, 0, 1. Yes, this is called the
Standard.
standard basis. Standard ordered basis. Okay, if you change the order, then it becomes a different basis. Okay, the order matters. You will understand why. Maybe in week 6, you will understand the importance of the order. Okay, the order is important for a basis. Okay. Any other basis?
60.
60. Okay. And then
011.
okay, fine. This is another basis. So like this, you can construct so many bases. Okay, for R3, what is the standard ordered basis for R3?
1, 2, 0.
0, 0, 1, 0,
0,
0, 0, 1.
0, 0, 1.
Okay, the usual notation for the standard basis is we don't tell it V1, V2, but instead we say E1, E2. For standard basis, this is the notation we are generally using, E1, E2, E3. Okay, so if you take any three linearly independent vectors in R3, that you know it spans R3, so it is going to be a basis of R3. Okay, so you take V1, V2, V3 linearly independent set, then that will form a basis. Okay, fine. Now for Mn of R, for example, maybe you let's first start with M2 of R. What is the basis? Standard basis, something similar to standard basis.
1.
1, 1, 0, 0, 0, and then 0,
0.
1, 0, 0,
Mm.
and then 0, 0, 1, 0, and 0, 0, 0, 1.
Okay, so this is a standard basis for Mn of M2 of R. Similarly, you can write for M3 of R. Okay, so homework, write it for M3 of R. Okay, it's not at all difficult. Similarly, you can write M3 of R, you can write. Okay.
But ma'am, it's now containing 4 vectors in R2, right? In a sense.
Okay, so kind of, so that you called as isomorphic spaces. So this you can kind of think of very similar to R4. That concept is called isomorphism, which we are going to cover in week 7. Okay, yes, you are correct. Some way you can compare with R4, but not exactly R4. You can compare it with R4. Okay.
Okay.
Fine.
Please, MNR1, can you please explain?
Mn of R is the set of all n by n square matrices. Okay. So
Can we construct for rectangular matrices also?
yes, of course, you can consider rectangular matrix also. So suppose if you are considering m by n of R, okay, that will still form a vector space. So this is addition, same scalar multiplication, that will still form a vector space. Yes, you can consider that as well. Okay, fine.
Ma'am, a question, ma'am. In the first case, ma'am, you have given the example, ma'am. If we take only three of them, not all the four, then will it be spanning and linear independent both? Means basis.
It will be linearly independent, but it will not span M2 of R. Just we have seen it here already, right? So here it is saying that span of S is a space consisting of all square matrices. It is incorrect because we see that there are several matrices which are not there in span of S. Okay, if you leave out one vector, one matrix, then it is not going to span entire M2 of R.
Oh, okay, ma'am.
Does that mean we need all four of them, right?
Yes.
Okay, ma'am. Thank you.
Okay. So is every spanning set of V a basis for V? What's the answer?
No, ma'am.
No, right? So for example, if you take 1 0 0 1 1 1, this is not a basis. This is a spanning set, but not a basis, right? Why it is not a basis?
It is a dependent.
Not independent. Not
Not
linear.
independent, so not a basis. Okay. Okay. Is every linearly independent set in V a basis for V?
No.
No.
There has to be
Must
spanning.
span.
Yes. So for example, if you just consider 1 0, so now this is linearly independent, but it does not span V. Does not span R2 here. Okay, fine. Okay, so what are some equivalent conditions for basis? The following conditions are equivalent for a set B to be a basis of a vector space V. So B is a linearly independent set and span of B is equal to V. B is a maximal linearly independent set. So this is the first statement is the actual definition. So this is the definition. The second statement says that B is a maximal linearly independent set. It means what? So any set which contains V, which contains B union some other vector. This is union. Okay, B union, I don't know, maybe I should write it in a better way. B and some other vectors. Okay, will become linearly dependent. That is maximal. It means what? Once you have the set, if you add anything to that, it will not be linearly independent. So that is called maximal linearly independent set. That is the maximum number of vectors you can have in that set B. If you add anything to that, that will become linearly dependent. That is mean by maximal. Okay. And what is mean by minimal spanning set? Okay. So what is mean by minimal spanning set? So suppose if
if we remove any
Any of them, then
vector
it will
from
not
it,
span.
then it is not a spanning.
vector from B is removed from B, span of B is not equal to V. Okay, B cannot span V. Then that is called minimal spanning set. So these are some equivalent conditions for basis.
So, ma'am,
Ma'am,
we can
excuse
say
me, ma'am. We can find that maximum linearly independent set is that we are able to find. We can, because there may be n number of linearly independent set, right? How can we find that maximum?
See, that is what I told you. So in R3, for example, I told you if you have 3 linearly independent vectors, that is the maximum number of linearly independent vectors you can have in R3. In general, for Rn, you know that n is the maximum number of linearly independent vectors you can have in Rn. So if you have a set of n linearly independent vectors, then you know that that is the maximal linearly independent vectors set, because adding any other vector, that will become a linearly dependent set, right? Okay.
We can take it either way.
Sorry, got it?
We can take that in that another way, right? The number of Rn will be there, no? Then n will be the linearly independent set, like that. We can take.
This is the maximum number of linearly independent vectors that can be in a set. Okay.
Then minimal spanning set can be any standard notation, or we have to find.
The minimal spanning set is also the similar thing you see. In Rn, you need at least. That is why we use the word at least. You remember? You need
Yes,
at
yes.
least
To
n vectors. For R2, you need at least 2. For Rn, you need at least n vectors to span the space Rn. Okay? Fine? That is why it is minimal. Okay. So here is an exercise. If V1, V2,
Ma'am,
yeah.
so we can see that this basis contains exactly n elements, and that is all of them are linearly independent, and that form the spanning set of Rn.
Can you please repeat?
So let's say that B is a basis of V, that V from Rn. Then so B contains n elements and all n vectors, and all are linearly independent.
So if your V is Rn, then yes, your B will have n linearly independent vectors.
Exactly, n linearly independent element,
Yes,
not
if
n
it is
less
a
or.
subspace of Rn, then the scenario is different. If your V is Rn, then what you said is correct.
Okay.
Fine. Okay. So exercise 4, maybe after this, okay, you have few more things. Maybe I will cover up to this point quickly. I'll not take much time, maybe another 5 or 10 minutes. If V1, V2, V3 forms a basis of R3, then which of the following are true? I will just do one, and based on that, you can answer the remaining. I will show you how. Okay, so first of all, for a basis, you know that you need 3. For R3, what is the condition we said? For R3, you need a set of
Minimum
3 vectors.
3 vectors.
vectors for a basis. So you are given 3 vectors in each of the case. So if you can show that they are linearly independent, then you know that you are having a basis. So how do you show that this is a basis? Okay. So for for linear independence, you know the definition. So alpha 1 V1 plus alpha 2 V2 plus alpha 3 V1 plus V3 is equal to 0. So now if this set is linearly independent, what it should imply?
Alpha I must be 0.
Yes, but that we don't know yet. So we are going to rewrite this as alpha 1 plus alpha 3 V1 plus alpha 2 V2 plus alpha 3 V3. Okay. Now you see that V1, V2, V3 is a linearly independent set, right? That is given to you. V1, V2, V3 is linearly independent. Correct or not?
Yes.
Yes, ma'am. Yes, ma'am.
Now you are having a linear combination of V1, V2, V3 equated to 0. What does that imply? The question.
Alpha 1 plus alpha 3 equal to 0.
Yes. So alpha 1 plus alpha 3 is 0. Alpha 2 is 0. Alpha 3
Alpha
is
3
0.
is 0.
So now alpha 3 is 0. When
Automatically
you
alpha 1 is
substitute
also
it here, it will imply alpha 1 is 0. So you see that alpha 1, alpha 2, alpha 3, all the coefficients are 0. So this means your set V1, V2, V1 plus V3 is linearly independent.
Independent.
So if it is linearly independent, you know that it forms a basis of R3, right? Okay. So same way, you can do the remaining 3 options as well. So I'll leave it as a homework. Okay. Is the basis of a space unique?
No.
No, ma'am.
No. Suppose B1 and B2 are 2 bases for V, then the number of vectors in B1 is
equal to.
Equal.
yes, is equal to the number of vectors in B2. If S is a subset of R5 such that span of S is equal to R5, then what is the minimum number of elements possible in S?
5.
5. 5.
Okay. Choose the correct options here. If S is a subset of R2 that contains only 2 elements, then S is a basis of R2.
Not all.
So that 2 must be linearly independent, right?
Yes.
Yeah, ma'am.
That is
Yes,
not
ma'am.
given here, so this option is incorrect. If a subset S of R3 contains only one element, then S can never be a basis of R3.
Yes.
True.
So at least you need 3 linearly independent vectors. Okay. Fine.
Yes, ma'am.
Option 3, if a subset S of R contains only one non-zero element, then S is a basis of R. We are talking about R.
Yes.
R, you can imagine
Ma'am.
the x-axis
Yes.
only. One
Yes.
non-zero element, will it
Yes.
span R?
Yes,
Yes.
ma'am.
Okay, fine.
Yes, it will.
Okay, good. If S1 and S2 are two bases of R3, then S1 is equal to S2. Is it true?
Not
No.
also.
No, it's not needed. It can be,
Uh,
but it's not needed.
Only the cardinality are same. The set need not be the same, right?
Uh,
Yes, ma'am.
Yeah.
so is there anything that is unique, like span is also not unique, basis is also not unique? So is
Mm.
there anything that is unique about the
And
span?
okay, R is actually R1.
Yes, yes, yes.
yes.
R
Okay,
means
okay.
R1. Is there anything unique, any concept which is unique you are talking? Dimension,
Uh,
dimension.
Dimension is, but like any set that contains unique element for a given vector space.
Ma'am, what is the difference between R square and XY plane?
See, XY plane means you are, okay, let me tell you. So, suppose you are talking about a paper. So, something like just only having 2 dimensions, that is R2. So, suppose you are considering your entire room and you are talking about one particular wall. So, now you are talking about R2 only, but inside a room. Okay, you are not just considering that wall alone separately, but the wall in the room. Okay, that is the difference. So that wall is kind of the xy plane, but now you are inside R3. The room is R3. Okay.
Okay, room is R3. What about XYZ axis?
XYZ axis, you look at any one corner of the room. So you have 3 lines in the corner of the room. That 3 line represents XYZ axis.
Okay.
Okay, fine. That you just have to imagine it. R3 is not like a very finite, which you see like a room, but like infinite room you have to imagine. Okay, fine. Okay.
Could you show the first exercise?
You mean the very first one or the first option of this?
No, the first exercise, very first one.
Okay, before that, let me just tell you what is dimension, and then I can formally wind up and then you can ask your doubts. So dimension of a vector space, the dimension of a vector space is nothing but the size or cardinality of a basis B of V. So the number of elements in your basis V is called the dimension. So any basis for Rn has how many elements?
N elements.
And
N elements, ma'am.
Dimension of Rn?
N.
and
N
N.
only.
Okay. So let W be a subspace of R3 spanned by this set. Now, what is the basis for this set? So is this a basis?
No.
This is not a basis, right?
so
So first we have to reduce, find the basis. So what can be a basis for W? If you consider this as a basis, this set can, this vector can still be
Yeah.
generated from this,
First
right?
two vectors.
removed.
So this you can consider as one basis. Now can you tell me what is the dimension of W?
2.
2. Okay. So
I'm
now
sorry, I couldn't understand. What is it?
see, now this is a spanning set, but this is not linearly independent. This full set. This is just
Okay.
some spanning set. So for dimension, you need to know what is the number of elements in basis. So first I'm
But
like
is it
reduce
really spanning? Because the z coordinate is 0 in all the cases.
set.
The z coordinate, I mean the z coordinate
See, it
in
is
all.
not spanning R3. It is spanning some subspace of R3.
Okay. Subspace of H.
So you are reducing the spanning set to a basis, and then you write the number of element in the basis. That's all. Okay. Okay. So maybe the remaining problems we will consider in the next session. So till now we have covered what is meant by dimension of a vector space.
Ma'am,
So
next session.
yeah,
When is the next session, ma'am?
the next session is on Sunday.
Okay, thank you.
Ma'am,
Okay.
are you going to take that session?
Yes.
Oh, thanks.
Ma'am, that first exercise, can you show again?
Yes. So exercise 1.
No, not this one, not this one.
Which one you are talking about?
That basis one.
This one.
Yeah. F4.
Any doubts in this?
Okay. No.
Okay.
Ma'am, I
Okay.
have a doubt
Yes.
about the matrices being vectors. So we saw that we needed 4 matrices to span R2 in a sense. It's the one above this.
Sorry. Your voice got disconnected. What were you asking?
Yeah. So we saw that we needed 4 matrices to cover to span R2.
Yes. Not to span R2. M2 of R.
Is it wrong to say it's R2? It's M of.
It's not R2. It's M2 of R. M2 of R is different from R2. R2 has only 2 entries, but here you are having 4 entries in each vector.
How do I geometrically or graphically imagine a matrix as a vector?
It's not possible. Apart from R2, R3, you cannot geometrically picture anything. So here you are having 4 coordinates. Anything beyond R3, you cannot picture.
Okay, so we are assuming that each of the entries is a coordinate, right, in the matrix
Kind
itself.
of. Yeah, kind of.
Okay, yeah.
Okay.
Excuse me, ma'am.
Yeah.
I have some doubt from the week 3 graded assignment. I can ask now or in the next session.
Please, for particular question, please ask the TAs in the TA session. Okay.
Okay, thank you.
Ma'am, I wanted to ask about a theory from week 3. Can I?